Every second, the world generates an ocean of data, but raw data is useless without the ability to extract specific, precise answers from it instantaneously. Suppose we need to find two specific numbers in a sequence that add up to an exact target, a challenge known as the pair sum. Or we might need to identify a single number that dominates more than half of an entire dataset, the majority element. When faced with these tasks, the instinctual method most beginners reach for is the brute force approach. Imagine an investigator trying to find a suspect by knocking on every door in a city, asking a question, and then knocking on every door again to double-check. It is exhaustive, repetitive work. While checking every possible combination guarantees you will eventually find the answer, relying on this method in modern software wastes massive amounts of computational power. Brute force tackles pair sum by checking the first number against every other. Repeating this creates a chaotic, tangled web. Similarly, finding the majority element requires building individual tally counters for every item, starting completely from scratch each time. In computer science, this mathematical trap is known as O of n squared time complexity. It happens anytime you run a loop of operations inside of another loop. With 10 numbers, the computer performs 100 operations. But if you scale that array up to 10 million numbers, the machine suddenly has to process 100 trillion operations. To handle real-world datasets, we have to abandon exhaustive searching. We need algorithms designed to look at the data exactly once. For the pair sum problem, we can replace the exhaustive search with an investigative technique called the two-pointer approach. There is one strict prerequisite for this strategy to work. The array of data must already be sorted in ascending order. Look at this clean array of sorted numbers. We place one indicator arrow at the extreme left, targeting the smallest value, and a second arrow at the extreme right, targeting the largest value. If the combined sum of these two pointers is greater than our target, we know the total is too high. We move the right pointer inward by one step to test the next smaller number. Conversely, if the combined sum is lower than our target, we move the left pointer inward by one step to test the next larger number. This systematic inward convergence zeroes in on the correct sum, either pinpointing the exact pair or mathematically proving that no such pair exists. By shifting boundaries based on strict logic rather than guessing, we solve the problem in a single fluid pass. This drops the time complexity to O of n and completely eliminates the chaotic web of brute force. Our second challenge requires finding a single element that dominates more than half of a chaotic, completely unsorted dataset. We solve this using Moore's voting algorithm, a method that tracks power dynamics across the data without actually counting the total frequency of any individual number. We can visualize this process as a balanced scale. The first number in the sequence drops onto one side, becoming the active candidate with a starting power of 1. Scanning from left to right, every time the algorithm encounters a number identical to the candidate, it adds a vote. A +1 weight drops onto the candidate's side, tipping the scale heavily in its favor. But encountering any different number introduces a hostile opposing force. The algorithm subtracts a vote, reducing the candidate's power and leveling the scale back toward the center. If the opposing numbers accumulate enough to drag the scale to absolute zero, an overthrow occurs. The current candidate is discarded, and the very next number in the sequence ceases control. Because a true majority element occupies more than half of the entire array, it is physically impossible for the remaining numbers to completely cancel it out. It will always emerge as the final survivor. There is one specific edge case to account for with Moore's algorithm. Its core logic strictly assumes a valid majority actually exists within the data. If we are searching a dataset where a majority isn't guaranteed, we rely on a simple failsafe. We run one rapid, single-pass verification at the very end to ensure the surviving candidate truly exceeds the halfway threshold. Looking at this split-screen comparison, the contrast inefficiency is stark. On the left, the brute force method creates a tangled, overlapping nightmare of redundant checks. On the right, the two-pointer and Moore's voting algorithms glide through the data in clean, linear sweeps. We didn't speed up the process by throwing faster hardware at the problem. We eliminated the wasted computational energy entirely by rethinking how we interrogate the data. Writing better code is rarely about writing more code. It comes down to the strategic application of logical forces, like convergence and cancellation, to outsmart massive datasets with minimal effort.